I don't know what was the last one from last week.
It started with mean at 1.
Yes. Yes, we started with this one, yeah, and then I showed you this other stuff, yeah, that was this. So, because last week I showed you that this additional stuff, that the Earth is totally differentiated. So that means we have the peridothitic mantle, yeah, I showed you this before as well. Then we have a continental crust, we have the oceanic crust. So, and then we have a lot of basalts, and here we have also analysis from a tonalite. Just by watching these analyses, then you can see that they are totally different, yeah? For example, the peridothitic mantle has much less SiO2 compared to the continental crust. We have here only 45.3 weight percent of SiO2, whereas the continental crust, we have 60.2. Watching the iron, we have here 7.3, here we have 6.3. Then the continental crust contains much more aluminium, whereas the peridothitic mantle contains much more magnesium, and the continental crust contains much more calcium, sodium, and potassium. Yeah. So, and that is, therefore, we are finding or we are forming on the continental side totally different rocks compared to the peridothitic side. I mean, to the mantle. Yeah. I mean, if you have a lot of calcium, sodium, and potassium, then we can form the feldspars, yeah, the feldspars, the plagioclases, and the K-feldspar. If we have a lot of magnesium, then we are forming, of course, a lot of olivine and a lot of orthopyroxene. So if you are looking for the oceanic crust that is actually the gabbros, yeah. And if you are going back to your field trip from ES203, then you remember from Yahuna Creek, there you found some gabbros, and the oceanic crust is from the chemistry. We have 48%, about 48% SiO2, that's nearly the same like for the peridothitic mantle. But the oceanic crust has then much more aluminium compared to the peridothitic mantle. Then we have a lot of calcium inside, because such a gabbro, we have a lot of anortite inside, and the anortite that is just a calcium-rich plagioclase. So then we are checking the basalt. The basalt is from the chemistry very close to the here to the oceanic crust. We have also a lot of aluminium, a lot of iron, a lot of magnesium, and even a little bit more than in the oceanic crust. We have calcium inside, sodium, but much less potassium compared to the continental crust. So then we have here the tonalite, and now we have once more the problem. It is this shit here, yeah. I mean, I'm throwing it now out of the window. The tonalite, and if you are going back to your ES106 field trip, then you remember the tonalite also from Yahuna Creek. And the tonalite, you know this by now as well, that is also a granite-to-heat rock. That is also a granite-to-heat rock, but the tonalite contains in its bulk chemistry much less potassium. Therefore, we are not forming, or we are forming much less K-feldspar. So now next slide, please. That we don't need. We don't need. So, Now I would like to introduce you into the binary system, or going from binary system into ternary system. So a binary system, that is just a line. And out of such a binary system, we can make a ternary system. So, but a binary system is just a line, as I told you just now, and therefore we can only span two components. In this case, we have quartz and quartz on this side, and on this side we have periclass. A periclass is just MgO. So the periclass that is just MgO. So, and therefore, if we have these two end members, we are talking always about the end member. If we have, from this point to this point, we have now two end members, and we can construct different minerals having MgO and SiO2. So, and if you are looking for in this Cartesian system here we have quartz, here we have the periclass. So, and then we have here one quartz, and here we have 1 mole of periclass, 1 mole of quartz. Then we can put, or we can have in this system actually 4 minerals. Yeah, we have here the pure quartz, here we have the pure periclass, and then we can make MgO plus MgO. That means the periclass plus SiO2. Then we can form here an MgSiO3. So, and that you know by now, that is an N-statite, but I gave you the formula in this way. That is Mg2Si2O6, because we have done all the calculations with pyroxides normed on 6 oxygen. Yeah, but that is then 50 to 50. So then we have from this line another mineral, and that you know by now as well, that is the mineral forsterite. And there we are using then a little bit more MgO. And we are using there 2. So, and then we are making a mineral, and that is Mg2Si O4, and that is then our forsterite. So, and that was the N-statite. So, and now we have a ternary system. Ternary stands for 2, that consists of these two end members, 1 and 2. So, next slide. So, but now we are going from a ternary system into from a binary system. Sorry if you are just going back. That was a mistake of mine. That is not a ternary system, that is a binary system. In a binary system, we have 2 components in space. So now we are going to the next. So now we are adding another component, and we are going from a 2-component space, from 2-component in space, we are going into 3 components in space, and therefore we are adding now a 3rd component, and that is in this case now water, and then we have now not longer a binary system, we have now a ternary system, And this system contains the magnesium, silica and water, and we are calling this the MSH system. So that means we have here a vector, we have here a vector, and we have here a vector. So in between these three vectors, we can span a triangle, yeah? We can span a triangle, and I mean a triangle that is then the ternary system. So if we are making a projection on a 2D space with three components, then we are using a triangle. So next slide. So that is then the way how it looks like. That is now such a triangle. And now we can calculate a certain mineral containing magnesium, silica and water. We can put in such a triangle, yeah? So in a typical mineral which contains then where's the... So a typical mineral which contains magnesium, silica and water, that you know by now as well, that is the mineral talc. So that is the mineral talc. I make here the shortcut talc, yeah. So and you know by now from our last class that is Mg3 Si4 O10 OH2. So that is the mineral talc. So and now we have this talc, and we would like to plot the talc in such a triangle. So and therefore we have then to figure out where this point is, yeah? So and now we have to calculate the xmg, the xH2O and the xSi2. So if we are calculating now the xmg, or xMgO, then we are taking all the magnesium divided by all the SiO2 plus all the water plus all the magnesium. So and now, how many MgO do we have in this formula? That was a question. Yeah, but not you must answer. So now we have here, as Neil told you, 3. Then you are making here a 3. Yeah? I mean the MgO number is the same like the Mg. Yeah? The oxygen we are just balancing. So and then we are dividing it by what? How many silica? 4, yeah. Four. Plus how many water? 2, yes. It is actually 1. So, and then how many magnesium? 3. So, and now you can calculate and tell me the result. So what did you get here? 0.13, yeah? Ah, yes, that was this, yeah. That is this 0.38, yeah? So then we are making the same with the X SiO2. So then how many silica? 4. And then we have below we have then 4 plus 1 plus 3. So and then what is the result? That is 1.5. So and then we have the same with the water, XH2O. That is then what? I make it here more clearly, and you can then tell me what you like to do there. So what should I write here? Yes, but at first, what should I write here?
1.
That we are doing then on this line. That is then 1 water. H2O divided by SiO2 plus H2O plus MgO. So, and then we have here 1 divided by 1 plus 4 plus 3. So, and what is the result? 0.13. That is not too difficult because it is already written here. So, and then we are putting such a line in a triangle, yeah? So, and now you have a ruler, yeah? Then just make a triangle in your book with a ruler, and you should make a triangle. You should make a triangle where the length is always the same and always 60 degrees. The angle between the alpha, beta, gamma is 60 degrees, and the length of all the axes is the same. So, because that is a thing where a lot of students have a problem. So just let me know when everybody has drawn the triangle. So Anil can then go now around a little bit and help them. Just let me know when you are ready with the triangle. So the lengths of all the axes should be the same. That means ABC it has the same length. And the angles here between should also always the same. So in this angle should then be 60 degrees.
I think most of you don't have a protractor, so this is what you can do. Draw 10 centimeter line, okay? Then mark 5 centimeter point. Just draw a vertical line. And then measure 10 centimeter where it cuts off, and it will be an equilateral triangle.
Yes. Then all the three angles should be the same, and all the lengths of the axis should also be the same. That is a very important point to draw such a triangle, because such a triangle is very important when you are write down later reactions, mineral reactions, yeah, because there we are using these triangles and they are very, very helpful. Yes, and if you have drawn the triangle, then you should subdivide the triangle in lines. So I told you, here the XMGO is 1. Here the XH2O is 1. And here the X silica is 1. Whereas here, the X silica is 0. And here the X silica is 0. Vice versa for the water. The X water here is 0. The X water here is 0. So and now you have to subdivide your triangle in lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. So because here we have an XMGO of 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, and here 0. So when these lines here, from here to here, they should be parallel to this line. So then you are subdividing the triangle here as well, with lines parallel to this line. Here, for example, we have an XSIN2, which is 0. Then here we have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Here the same for the XH2O. Here on this line, along this line, XH2O is 0. Then we have 0.1, 0.2, 0.3, 0.4, 0.6, 0.7, 0.8, 0.9. So, and now you should have you drawn in all these lines. Yep, have they drawn in these lines.
Yeah.
So, and now you got these three numbers, yeah? We got an x and g force of 0.38. So, and then you are at the x and g o for here is 1. Here it is 0. Then we have 0, and we have a number of 0.38. Then it is here 0.1, 0.2, 0.3, 0.4, and then it should be somewhere here, a little bit beneath 0.4, and then you are drawing a line parallel to the line here at the bottom. Yeah? Just draw a line, it's important. And the same game you are doing for the XH2O and also for the same you are doing for the XH2O and also for the XSiO2. So, and if you have drawn in these lines, and if you have made it correctly, then the lines must cross, all three lines must cross in one point. So if they are not doing this, then something is wrong. Because if you are adding this plus this plus this, then you must get a number of 1. Yeah? So then you must get roughly, and I make here the roughly sign of 1, because we have rounded up and rounded down. Yeah? I mean here the 0.38, that was actually a 0.375 or something like this, and here that is also a little bit below, and then you get a number of 1, because it's always like this with three components in space. You have then always a number of 1. And we are calling this in petrology a chemography. So just tell me when you are done, but that has to be done carefully, because that will follow you the whole class here. And also, yes, that is correct. Yeah, you got it. Yeah, it's actually totally simple. Yeah. And for those who are doing next year the ES301 and the ES303, you will always confrontate with this triangle. Because if the triangles or the points which you are plotting in such a triangle are wrong, then later on all the reactions resulting from this are also wrong. And then the whole study is wrong. So, are you done? Yes? Then we are going to the next slide. So that is just another method how you can plot such a point inside. I mean, you can also do it by using the cosinus, yeah? You know this function on your calculator, and you have done it in school. But I would suggest, I mean, it is up to you, and you can do it for yourself. Maybe if you are getting bored, yeah? Then you can try this as well. I mean, the result is the same, but I'm preferring actually the method which I showed you now, because it is just much more easier and much more faster. So next slide. So now we have here a ternary system, and we have the binary system. So I mean, we have here the same triangle as before. We have here now at the top H2O, we have MgO, and we have SiO2. So, and then here on this line we have the binary system between MgO, that is the Perry class, which I just told you now a couple of minutes ago, and here we have the quartz. So then, of course, here in the binary system, as I told you before, we can plot the mineral forsterite and the mineral enstatite, yeah? So, but now we are a gardener, yeah, with a can, walking around on the ground, and then we are hydrating our Harzburgite, you know by now, that the rock, which is called, contains forsterite, and enstatite is called a Harzburgite. So we are walking around on the ground, yeah, blah, 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 and then we are hydrating all this thing, and then we are forming hydrous minerals, yeah, or we have already all these hydrous minerals, and we are dehydrating the hydrous minerals. So that means we have following situation. So going back a little bit to geology, yeah, and maybe not only chemistry, but geology, unfortunately, that is chemistry. So we have here our dipping slab, yeah? Here we have just our middle ocean ridge. You know this picture by now, yeah? So here we have our slab. So here above we have our oceanic crust. And here we have our mantle slab, yeah? So, and that is the oceanic crust. So, and that is our peridotite here, yeah? So, in this peridotite, there we have lersulites, we have harzburgites, and we have dunites. So, and all these rocks are formed. Some were here by a magma at the middle ocean ridge. So, and therefore this plate is moving to this side, and this plate is moving to this side. We have here a spreading center, yeah? So, and now we are making the the continental crust, and the continental crust is more cold, yeah, more cool. Therefore, I'm making it a blue, yeah? It's like as I told you last week with the tap here, yeah, not with this one, that is for the tap, that is the eye wash, yeah? And there it's everywhere the same temperature, so you will not wash one eye with cold water and the other one with hot water. So, but anyway, on the tap you have red, that is hot here, blue, that is cold here. So, and that is then the continental crust here, yeah? So, and now, and that is a very important thing, yeah? That is now very important. When you are forming here your oceanic crust, and beneath you are forming your peridotite, yeah? And here beneath you have your pyrolite. Pyrolite, that is just a theoretical composition constructed or developed from Ringwood in 1967. So, and here we have then the water above, yeah, that is the ocean, yeah. Therefore, we are making here a ship, and we know that this is the ocean. And here we are going beneath the water, and therefore we are making a fish. So, but anyway, the rocks which you are forming here, they are totally dry. Here you have a totally dry harzburgite, yeah? Totally dry harzburgite, consisting here of this forsterite and this enstatite, yeah? So, in the lersulites which you are forming there you have then additionally calcium inside, and there you have then additionally clinopyroxene, and we have plagioclase, or at higher pressures it could have what can it have at higher pressure? Spinel, and then we have the garnet. So, but that we will discuss later. But now we are just doing it in a very simple way. You have the forsterite and the enstatite. So, and now I told you we are making from this forsterite and enstatite, the so-called harzburgite. We are hydrating this rock, yeah? We are hydrating this rock, and for hydrating this rock we need water, yeah? So, and if we are just going here to the ocean, of course, then we just take the oceanic water above, yeah? So, but now there we have a cover, and that is the oceanic crust. I mean, the oceanic crust becomes also hydrated. So, but beneath the oceanic crust, we have this mantle slab, yeah? So, and this mantle slab becomes not totally hydrated. It becomes only partly hydrated. Because otherwise, we could not subduct the whole thing. If the whole thing would be totally hydrated, then the density would be lower compared to the continental crust. then we would not subduct the whole thing, then we would abduct it, yeah? So I mean the reason that we can subduct this mantle slab or the oceanic lithosphere, yeah, being scientifically totally correct, then we are not talking always about slabs, then we are talking about the oceanic lithosphere, yeah. So, and that we can subduct this oceanic lithosphere, well, the reason is because the oceanic lithosphere has a higher density compared to the continental crust, yeah? You know this by now. So, but, and if too much is hydrated, we have here ATG, that is our mineral antiborite, yeah? And you know by now an antiborite that is just a very hydrated mantle rock, and then you are forming an antiborite. And this antiborite that is serpentine. So if there are huge portions are hydrated and you are forming antiborite, then this oceanic crust has a lower density compared to the continental crust, and then you will not subduct it, then you will abduct it, yeah? So then the then this mantle slab will not go in this direction, the mantle slab will then lie here around, yeah? Because it has a lower density then, yeah? So, and these are ophiolite complexes, and such ophiolite complexes you can find on a lot of different places on this planet. So, in the next ophiolite, which you can find here around the corner, where do you think is this? Where do you have here in the South Pacific high-grade metamorphic rocks? Here in Fiji, you do not have high-grade metamorphic rocks because they are still far away under our feet. If they are there, yeah, I'm not sure if they are even there. But here in the South Pacific, where do you have high-grade metamorphic rocks? Blue schists, eclogites, amphibolites, and ophiolites. This is in New Caledonia. There you have them, yeah? So, but anyway, now I got away from that what I would like to tell you, but now I will tell it to you what I like to tell you. Yeah, that is now the ophiolite, and that is New Caledonia. So, but what do you need to hydrate these rocks which are located here? I mean, the water must come from here somewhere there. How will you do this? That you are doing via cracks. So the whole oceanic crust has cracks. If you are just checking here this picture, here you have everywhere perpendicular to the middle ocean ridges cracks. If you are going back to your ES203 documents, there is one PowerPoint or one slide in one PowerPoint where you have this situation where you can see the ocean floor, yeah? So, and if you are too lazy to go back to your PowerPoint, then you can just use Google and put in searching for ocean floor, then you get hundreds of images within a second, yeah? So, and then you can see everywhere these cracks. So scientifically, we are calling them not only cracks, they are then called faults. So, and then we have here on this image, we have only this, there are only these faults are showing which are perpendicular to the middle ocean ridges. So, but perpendicular to that fault, you have also other faults, yeah? So, and on high resolution images, you can see this. So that means you have these cracks here. So in these cracks, here is a crack, maybe here is one. So, and through these cracks, hydration will take place. So, because the oceanic water goes down there, yeah? So, and then hydration will take place, and then you are hydrating your mantle rocks and the oceanic crust above. So, and now you are sending your whole sequence down here. Yeah, you are just sending it down here, this way. So, and what happens then there? I mean, here it is hot, and here that is the mantle wedge, there it is also hot. What happens then there with your hydrated cracks? They are becoming then dehydrated, yeah? So, and then you are forming again your forsterite and enstatite, yeah? So, but before metamorphism can take place here, you have at first to hydrate them and later on dehydrate them. So these mantle rocks from here and from here and from here, they will not undergo metamorphism, because when they are totally, if a rock is totally dry, then nothing happened. Absolutely nothing. So that metamorphism can take place, you need always volatiles. So, and then you are forming there, while you are in first stage, you are hydrating them then, and then you are forming their different minerals. Here you are forming an antophyllite that is an amphibole. I will show you next Wednesday in the practical, because I'm doing next Wednesday the practical, because now we have also reached the amphiboles. And then we can make a sheet where we put all these mineral chemical formulas together. Then you have all of them. So, but anyway, such an antophyllite, yeah, antophyllite, that is then, I make just a shortcut here. That is an Mg7, Si8, O22, OH2. That is an antophyllite, yeah? So, and then the antophyllite is plotting here. Then here we have the type. The type you have just plotted in this triangle before, yeah? So then we are putting more and more water on it. And if you are going to your documents, I think this one is also uploaded. Yeah, it is, yeah. Yeah. Just summarize it that we have our own 2017 folder. Because now the whole thing is very full from all the last years. So, if you are putting more water, and you know by now that the antigorite has an OH4 group, yeah, it's more water inside. then the antichloride is plotting here, and here we have the blue side. So, and now we are doing a funny thing. Only that you understand why we are doing this, yeah? Because otherwise you are thinking, yeah, that's nice to have such a triangle, but for what? I will show you now for what. So we have now this system that is a very easygoing system, yeah, between these three components in space. That is water, MgO, and SiO2. So, but now we would like to form a talc. Yeah? Walking around on the ground will forming a talc. So that is not only for minerals, that is for everything, for every chemical reaction. You can use such triangles, but it is actually developed by metrologists. Now we would like to form a talc. So, and if I'm asking you, or Neil is asking you in the test, you should write now the chemical or the reaction from a talc. So, and then you are sitting there and then you don't know what to do. But it is totally simple. So, we would like now to form a talc. And then you are drawing your triangle. So, and now the simple thing is you are forming a talc. Then you are just putting your hand on the talc, yeah? So, and then we have a system to form a talc, and then you are using a triangle method, enstatite plus water plus SiO2 is talc, because the talc is lying inside this triangle, yeah? So if you have now done your drawings wrong and your talc is plotting there, then you will be done, you have the reaction forsterite plus water plus periclase, but it is then not balanced. So therefore it has to be correct, yeah? You are just putting your hand on the talc, and then the talc is inside this triangle, enstatite, water, SiO2. So, and then the reaction is finished. You have the talc, you are using enstatite plus SiO2 plus H2O. So then you know the formula from talc, that is Mg3, Si4, O10, OH2, the enstatite you have MgSi3, O3, plus the SiO2, plus the H2O. So here we are not writing it like this, because that is a quartz. And here the H2O we are not writing like this. We are making just a W for water. So now we have to balance the whole thing. We need here 3. Then we are putting here a 3. We have 3 magnesium. We have here 3 silica, 1 silica is left, we are using this one. So in the rest we have here 9 oxygen, 9 oxygen, plus 2 is 11 oxygen, plus 1 oxygen is 12 oxygen. What we have here, 10 oxygen, and here the O, 12 oxygen, and we have then 1 water. So, and therefore we are using these triangles. So, and now just to make an endophyllite. You are putting your fingers here on the endophyllite. So, and then how can you form then now an endophyllite? Or you are putting your hand on the endophyllite. So, and what is then the reaction to form an endophyllite? Now, the endophyllite is directly lying on this line between talc and enstatite. Then enstatite plus talc is endophyllite. So yeah, next slide. So, but with these triangles, we can also spend our mineral chemical vectors. I told you, I think, since the beginning, I told you, you have in minerals also chemical exchanges. So, for example, if you are looking for the olivine or for the autopyroxene, I mean, here we have the olivines, here we have the autopyroxenes, here we have the autoamphibols. There we have an exchange vector inside these minerals, and that is the Fm exchange. So, in the Fm exchange, I told you this, that is the iron magnesium exchange, yeah? Because I told you, for example, a magnesium-rich olivine is formed at higher temperatures or high temperatures, whereas an iron-rich olivine is formed at lower temperatures. So, and if you are looking for the autopyroxenes, it's the same. The enstatite is a magnesium-rich autopyroxene formed at higher temperatures, whereas a ferrocylite is an iron-rich autopyroxene formed at lower temperatures. So, and if you are now looking for the endophyllite I just gave you the formula here, that was this Mg7, Si8, O22, OH2 amphibole. There we can also do an Fm exchange, then we have just an iron endophyllite. So, there you are using then just the triangle, which contains iron, magnesium, silica, and then you can plot your olivines, your autopyroxenes, and your autoamphiboles, yeah? So then we are going to the next slide. So now we are going back to our MSH system, which I showed you just right now. So here we have again the ternary system, here we have the binary system, here we have our Harzburgite. If we are walking around with a can, or in reality we are hydrating this Harzburgite in the metal slab, then we are forming serpentine, and this serpentine which we are forming, that is then the antigorite or the chrysotile, depending on the temperature. So, and that is then the composition of the mantle rocks that is here in this field, in this one. So, and here you have again all these hydrated possibilities of your mantle rock. So now we are going to the CMS composition diagram. So now we have kicked out the water from our space, because if we are talking about the ternary system, we can only talk about 3 components, yeah? So because the triangle has only 3 corners, yeah? That is so. It's just in the nature of the things. So therefore we are putting then water in excess, and then we are just writing there plus H2O, and here I have also written plus CO2. But if we have now a CMS composition diagram that is consistent of quartz, CaO and MgO, and here I have written CO plus CO2 in excess, because the mineral which we are forming here, that is the mineral calcite. Yeah? You know, CO2 plus CaO will give you a calcite, which is a CaCO3. So, but now having calcium in the system, we can form some other minerals, the diopside and the tremolite. So in the diopside, you know by now, we have done the pyroxenes in class, yeah? The formulas. Yes. So in the diopside, that is the clinopyroxene, and has the formula Ca, calcium, magnesium, Si2O6. So that is now our diopside, yeah? So, and therefore we can spell out this greenish field. So in this greenish field, these are the lersolites, yeah? So in the lersolites, these are then these pteridotites containing additionally clinopyroxene. So, and they are also formed at the Middle Ocean ridge, together with the dunites and the Harzburgites. So in the tremolite, that is then the clinoamphibole, that is the tremolite, that is Ca2, Mg5, Si8, O22, OH2. I will give you all the amphiboles the next week in the practical. So, and if you are forming such if you like to form such a tremolite, you are putting the hand on the tremolite, that it's diopside plus tile plus the water which is in excess will give you tremolite, yeah? So, but here we have then the lersolites in the greenish field. Here in this bluish field, we have the composition of the majority of the mantle rocks. So, and that is the thing what you can then show in the CMS system. And if you are writing this down, then you can construct your mineral chemical reactions. out of this. So now I have to do it by myself. So now we are going back to simple phase relationships and how it reflects the atomic structure. So the most simple and the most famous phase diagram, that is actually the phase diagram of water. So because the phase diagram of water is shows very easily, or it is very easily to understand the things about the entropy and about the enthalpy, how the volume is changing, how the density is changing. So because if we are sending rocks down, so then we will increase the pressure on this rock. Yeah, we will just send it down. We will increase the pressure and we will increase the temperature. So when thereby we are increasing the pressure, what happens then to your rock? What happens to your rock or to your mineral? I mean, if I'm putting you guys in a huge press, gave 10 kilobars on it, what happens then? You will become smaller and smaller and smaller. So that happens to a mineral as well. So and while you are becoming smaller and smaller and smaller, that means the volume of yours will decrease. So what happens then with the density? Density will increase, yeah? I showed you this at the beginning of our class also, while we did a diagram of quartz with the different varieties of the mineral quartz. So you have the alpha quartz, the beta quartz, you have the borisite, and you have the schistolite. The schistolite has a much higher density compared to the alpha quartz, yeah? So that means the volume will decrease, the density will increase. So these are two parameters now, yeah? So, but now we are going back to the water, because with water you can see this very easily, because I don't like to heat you up. So, but if you are putting a pot of water on your stove, yeah, on your oven, or you are heating the water up, what happens with the water? It becomes spoiled. So, and then you are making from liquid steam. So, and what is happened then to the volume? The volume will increase. Yeah? The volume will increase. So these are very, and the density will then decrease. So these are very, very simple relationships. So and now I'm introducing the entropy. We will talk about the entropy a little bit more in detail, because we will also give Steve some exercises using the entropy and the enthalpy and the Gibbs free energy to calculate some stability fields of minerals. Most students hating it like hell, but I love it. So anyway, you have here the structure of ice, yeah? So yeah, there you are, and you know how you have hydrogen and oxygen, yeah? So here you have the oxygen, and here you have two hydrogen, yeah? So if you are heating up this ice and you are making water out of this ice, let us make it easier because there is the anomaly of water. Yeah, you know that ice has a lower density compared to water. Yeah, therefore an ice, how is it called? An ice mountain is swimming. Yeah. Huh? Iceberg, then it is like in German. See. So. Then it is swimming, but anyway, we are heating now up, we are making water out of our ice, then we are heating up and boiling our water, making steam. So, and what is then, what you are thinking is with your, happens to your hydrogen. I mean, you know by now from the classes before and from school before, that these atoms are not fixed, they are swirling around, yeah? So, and if you are heating up the whole thing, the volume becomes bigger and bigger. So, and then what happens to the atoms? They are swirling bigger and bigger circles, yeah? So, and that is the entropy. That is the entropy, and that means if a mineral has a higher entropy, or with increasing temperature, the entropy will become higher, and the next thing, the volume will increase, and the density will decrease. If you are putting pressure on it, then the opposite thing is the case. Then you have another thing, that is the enthalpy. That is the heat capacity. So how many heat can be stored in a rock or certain material? So if you are looking for metal, yeah, iron, and if we are comparing iron with, how is it called? Porcelain, is that the same like in the English? Porcelain, yeah. Porcelain, yeah. You know where the cooking plates and all this stuff is, yeah. So which of these two materials, iron compared to porcelain, can store more heat? Iron, yeah. So and that is the enthalpy. So and here we will do some exercises, so we will do it together because when we are doing the exercise, then you will understand the things better. So that means here you have your hydrogen bridges going back to water. If you are heating up the whole thing, the atoms will swirl more around. The volume will increase. Next slide. So and there we have now the phase diagram of water. We are putting in petrology always normally, not all people are doing this, but I'm doing this like this way, other people doing this the other way around. Some of them, they are flipping the pressure on the negative side, yeah, because we are comparing the pressure always with the depth of the earth. They are putting then the pressure axis somewhere here, yeah. So and then the whole thing is then on the head. But I'm preferring this way. We are putting here the pressure like this and the temperature like this. So then we have here the water diagram, yeah, H2O phase diagram. Then we have here solid, and that is ice, yeah. We are heating up the whole thing. Then we make here liquid. So in liquid, that is then just water. So and then we are, here we have doing the same as a constant pressure, and the constant pressure here, I think we are using here just atmospheric pressure, that is one bar. So and here we have then the melting point. That is then at 0 degrees Celsius, yeah? So here we have the boiling point, and that is when you are making in your cooking pot steam, yeah? That is the boiling point. yeah? So, but now we have here a critical point. So, because I told you and that is a top thing nowadays in research, since the last, not that long, maybe 10 years, no, more than 10 years, maybe since the last 20 years, there is a topic in research, and a lot of people working on this. And because people would like to know how many water is in the Earth's mantle. You know by now, I mean, I showed you just a picture before, and you know this picture now thousands of times. The oceanic crust becomes subducted beneath the continental crust. And I told you right now as well, a lot of water is going down via the subducting slag. And most of the water is hosted in the sediments above. So in the sediments above, they are very, very wet, yeah? I mean, of course, the sediment in the ocean is always very, very wet. So, but now you know by yourself, here we have the boiling point 100 degrees Celsius. So in the Earth's mantle, we are dealing with much higher temperatures. So in there, the water is not longer as a fluid phase, it is like a plasma. So here we have, it is not longer a liquid phase, it is a fluid phase. That is the thing, yeah? Sorry for telling you sometimes totally weird things, it is a fluid phase. So and that is after this critical point, and the critical point is by 273 degrees Celsius. So and then the water is in our mantle, it is around as a fluid phase. So and one can calculate this and one can measure it, how many water is in the Earth's mantle, but we figured now out that the Earth's mantle is actually totally inhomogeneous, yeah? Niels showed you yesterday this eclogite, yeah? And there you could see in one sample that the eclogite on the front side looks different from that from the back side, yeah? So because the eclogite on the front side or back side, I don't know in which way you were watching it, but there one eclogite that was a more greenish, more reddish one, that is then the B-mineralic eclogite, and the one on the other side that was kyanite-bearing eclogite. There's additionally the mineral kyanite inside. And this kyanite is actually a water-free mineral. I can give you next week a talk about this, yes. That is maybe also a good idea for my own research, which I have just published right now. It just came out in March from such a sample which Neil showed you yesterday. And only parts of this eclogite has been transformed in a B-mineralic eclogite, and other parts not, because there was not enough fluid available, yeah? So if you are looking then while we are doing our field trip, we have still to figure out when we should do the field trip, yeah? If you are looking at this core sample, and Neil is working on these core samples, and we found there is no water inside, yeah? So, but in other mantle rocks there is a lot of water inside. So, and that shows you how inhomogeneous the Earth's mantle is, yeah? So, and these inhomogeneities from the Earth's mantle, that leads then, I mean, on the other hand, to the formation of wealth. If you like to create wealth, you need water, yeah? Otherwise, you cannot create wealth. So, and then you have a beautiful volcano where you can go during the night and watching it and waiting till you get a bomb on your head. Or you can have an earthquake, yeah? So I mean, to create an earthquake, we need always stress somewhere in the Earth's mantle, and that is all controlled on a very, very micro scale, yeah? And this microscale that goes down to the atomic structure. So, and therefore water is very important to run all these things. So, but anyway, here we have a very simple phase diagram, and that is the phase diagram of water. We have here solid, we have here liquid, and here we have the fluid phase. Next slide. So, and of course we have the different modifications of our ice, formerly ice and then water, and that depends also on the pressure, because while we are putting more and more pressure on it, that means we are compacting the whole thing, and then we will decrease the volume and increase the density. So, and there you can, if you are using CO2, and which is a gas, yeah, and you are putting a lot of pressure on it, then you can make from CO2 dry ice. So, next slide, please. No, that is the last slide. That was not that was the ice phase diagram. So, and if you are putting more and more pressure on it, yes, then you will decrease the volume and increase the density. So, yeah, next slide. So that is then the water triple point. These are just easy relationship. Here you have the ice, here you have the liquid, and if you are going up there, you have steam. So now you are shocked by these numbers, but you must not be shocked because that is in Kelvin, yeah? Yep. So what kind of mineral is this now? That is, that is the coordination polyhedra. So, and I mean, atoms are always controlled by the radius of the atoms, so that you can fix them together. Of course, and here we have a relationship. Here we have here maybe 4 oxygen. Here I don't know what we have here. Because that is not a tetrahedron. Maybe we will know this later. I will figure it out. Can't remember. Yes, now I remember. That was salt, yeah. So that is salt, and you know the salt, halide, that is sodium and chlorine, and halide, that is, natrium chloride. So, and that is a cubic mineral, yeah? So if you are growing salt crystals, so do you know how to grow salt crystals? That you can also do in your cooking pot, yeah? You are putting water in your pot, and then you are putting a lot of salt inside. Then the salt will become dissolved in the water, yeah, like in the soup, yeah. So, and then you are heating your pot up. So, and then you are producing steam. And the steam will become removed from your pot, yeah. So, and then you have at the end, you have salt crystals. So, and then you can just take a hand lens, and then you can watch your salt crystals, and then they are looking like a cube, yeah? So, and that is now the go to the former slide. That is the coordination polyhedra of salt, yeah, next slide. So, and there you have the sodium, which is the red bubble, surrounded by chlorine, which is the green bubble. Yep, next slide. So, that is now a low quartz. Well, these are the polyhedron, the tetrahedrons. how they are related to each other in a low quartz, and that is the alpha quartz, which we can find on the Earth's ground. So in the low quartz, that is actually a hexagonal mineral, and maybe can you just bring us some of these quartz crystals? So just that we can compare with what we are seeing here, that one can actually see it also in nature. So that it is then not a little bit too abstract. So, but you know now, we have done this in the weeks before. A quartz contains only of silica and oxygen, and the silica is sitting inside the tetrahedron. Yeah, you know this by now. It is sitting inside the tetrahedron, and here the oxygens are sitting outside. Yeah. So, and then we are connecting these tetrahedrons, every corner of the tetrahedron with another tetrahedron, and then we are forming a quartz. So, and that is the quartz, how it looked like, how it looked like at the Earth's surface. Yes, and Neil has now some quartz crystals. Yes, that is great. So here, that is a wonderful thing, yeah? So, and if you are watching these quartz crystals here, yeah, they have grown in space, not in outermost space. I mean, they have grown here somewhere on Earth, but they had a lot of space to grow. So, because then they can develop their crystallographic symmetry. So, and if you are just checking it and giving it around, then you should be easy then you should be able to tell me where you can find in this atomic or in this tetrahedron model where you can see the hexagonal structure from these quartz crystals. I mean, you can see that they are hexagonal, yeah? They have 6 corners. 6 corners. So where can you see this in this tetrahedron model? Here you can see it. 1, 2, 3, 4, 5, 6. Everywhere. 1, 2, 3, 4, 5, 6. So here you have your hexagonal arrangement of your tetrahedrons, and that you can see now in the crystal which you are holding just right now in your hand. So, and that is now for the low quartz modification, or also called the alpha quartz modification, which you can find on the ground, as you can see here in this hand sample, or hand specimen. So, but that is now the low quartz. So now we are putting pressure on your quartz, yeah? We are just throwing this quartz crystal in an orogeny. An orogeny that is just a collision of continental fragments. And if we have the collision of continental fragments or of whole continents, then we are forming a mountain belt, and therefore we are forming high-grade metamorphic rocks. So, and if we are putting the pressure on your quartz, increasing the pressure, then your quartz will become deformed and become smaller. So, but we can also take this quartz and heat this quartz up. Then we can just do in an experiment. Heating it up, going to, I don't know, 700 or 800 degrees Celsius or even more. Then the volume will increase, yeah? The density will become lower, and then you are forming here the tridymite, that is another quartz variety. And you can see the tetrahedrons becoming then more loose because the volume increases. So whereas when we are going to the next one, I hope I have a picture. Now that is the cristobalite, that is then not longer hexagonal, but you can see how the symmetry changes with increasing temperature here, yeah, in this. But now I hope I have one where we can see the, yeah. Here we have the low quartz, which shows much more loose bonds, yeah. And here we have the high quartz, because there we are increasing the pressure and the temperature. Yes, here we have our phase diagram. You can see here you have shown before the tridymite, the cristobalite, yeah, I mean in this atomic structure. Here we have the low quartz, that is this one which you have just holded in your hands. The high quartz, if we are just increasing the pressure, we are forming a coesite, having a higher density compared to the low quartz, because the volume becomes, or the volume will decrease. So, and then we are increasing the pressure again, and then we have a stisovite. So, and now we are done for today.